In this problem, we're given a resistor network circuit, and this is hooked up to a battery. And our battery actually has internal resistance in it that's given as 50 milliohms. And I'm going to go ahead and express that in ohms real quick. That's 0.05 ohms. And the terminals of the battery are labeled as A and B. And actually, in part C of the problem, we're going to be asked for that terminal voltage between the two terminals of the battery. That includes the voltage drop over the internal resistance. Now, the rest of the circuit is just 4 resistors, and it's a combination of series and parallel. So I have 3 that are clearly in parallel, R2, R3, and R4. And that parallel combination is in series with R1. In part B, we're asked for the total current in the circuit. In part C, we're asked for the terminal voltage of the battery. And then in part D, we're asked a power question. We want the power dissipated by R3. So the approach to all these resistor network circuits is to start simplifying by using the parallel and series resistor combination rules. And at each step, we're going to combine some resistors using one or more of these rules, and then we redraw the circuit. We get it simpler and simpler until there's only one equivalent resistance left. That allows us to compute the total current, and then we work backwards through the circuit. So I'm going to start with this parallel combination, R2, R3, and R4. Those are all in parallel. And I remember that 1 over the equivalent resistance for a parallel combination is given by the sum of the reciprocals of all these resistances. And there's not room to show every little calculation here, but I plugged into my calculator 1 over R2, that's 4.7, plus 1 over 1.5, plus 1 over 1.5. I hit enter, and then I took the reciprocal of the result to get the equivalent resistance. And this comes out to 0.6468 ohms, just keeping a little extra precision in the middle of this process. Now we redraw the circuit with the parallel combination simplified into a single equivalent resistor. And that's what it looks like. Now I just have 3 resistors in the circuit. There's the internal resistance of the battery, the original 4.7 ohm resistor, and then the parallel equivalent of those 3 resistors that were in parallel. So for the next step, I recognize that these 3 resistors are in series, meaning that they share the same exact current. And to combine resistors in series, I simply add them up. So R total is going to be the sum of these 3. So I'll write that as little r for the internal resistance, R1 for the 4.7 ohm resistor, and REQ for the parallel combination. And when I add all these up, I get a total of 5.397 ohms. Now we have the total equivalent resistance for the entire circuit, and I can redraw it as a simple circuit. And our ideal voltage, or EMF, is still 1.5 volts. The total resistance, including the internal resistance of the battery, is 5.397 ohms. And this is the point where I can start to make progress and work my way back. So having a single ideal voltage source and a single resistor allows me to use Ohm's law to compute the current. And I'll just move down to part B on this because that's where it was asked. And my total current is going to be V over R. That's just turning Ohm's law V equals IR around. So I have a 1.5 volt EMF, and then I'm dividing by 5.397 ohms. And this gives me 0.278 amps. So that's the total current flowing in this circuit. I can visualize it like this. It goes from the high side of the battery to the low side. There's my total current, I. Now, if I work my way backwards from my simplest circuit to the one in the middle, the simplest circuit resulted from the simplification of 3 resistors in series. And resistors in series all have exactly the same current going through them. And that means that same current, I, or 0.278 amps, must be flowing through that circuit in the middle picture. This allows me to quickly answer part C. I want the terminal voltage of the battery. And that's just the ideal voltage, or EMF, of 1.5 volts, minus the voltage drop that you get over the internal resistance. And that voltage drop is just given by I times R. So 0.278 amps is flowing through that internal resistance. And the value of the resistance was 0.05 ohms. And I should be able to find the voltage drop over that internal resistance. When I run the numbers on this, I get 0.0139 volts. So the terminal voltage is just going to be my ideal voltage minus that internal voltage drop. If I want to get more formal about it, this is how you could reason through it. I would start at A, and I would say VA plus the rise in voltage across the EMF, that's 1.5, minus the voltage drop across the internal resistance has to be equal to VB. And the terminal voltage is formally VB minus VA, and we normally just call that VAB. And it should agree with your intuition. That's just the ideal voltage minus the drop over the internal resistance. 1.5 minus 0.0139. And when I run the numbers on this to 3 significant digits, I get 1.49 volts. So there's just this little bit of a drop because of the internal resistance. Finally, in part D, we want the power dissipated by R3. And there's more than one way to go about this, but the most efficient way to do it is to just find the voltage drop across these parallel resistors. So in my middle picture, I have this equivalent resistance of 0.6468 ohms. That was the 3 parallel resistors put together. What those share in common is having exactly the same voltage drop across them. So all I have to do is get the voltage drop across this equivalent resistor, and that is going to be equal to the voltage drop across each of these in the parallel combination. In particular, it will be the same as the voltage drop across R3, which is the one I'm interested in. Now, once I have R and V for that resistor, I can get the power. So how do I get the voltage drop across the parallel equivalent resistance? I have the current as 2.78 amps. In this intermediate circuit, the current cannot be split anywhere. It all flows through that equivalent resistor. And I have the resistance of that equivalent resistor, 0.6468 ohms. Into 3 sig figs, I get 0.180 volts for the potential difference across those parallel resistors. Again, that's the same as it is for each individual one of those parallel resistors. So now that I have the resistance of R3, that's 1.5 ohms, and the voltage drop across it, that's 0.180 volts, I can compute the power. Most fundamentally, the way we compute power is by taking I times V for whatever circuit element we're studying. But for resistors in particular, you can use Ohm's law to substitute into this. So the thing I don't have for this resistor is I. I could quickly compute it, of course, by using Ohm's law back at this step. But to avoid that, I can sub out and replace I with V over R using Ohm's law. When I do that, I get this power formula, V squared over R. And that formula applies only to resistors. I plug in my potential difference, 0.180 volts. That's going to be squared, divide by the resistance, 1.5 ohms. And when I run the numbers on this, I get 0.0216 watts. Now, it's common when we're studying circuits to move our answers into a little nicer form by using SI prefixes. So it would be more common to see this answer as 21.6 milliwatts. And we're done. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.